Welcome to Mechanical Explorer. In today's video, we discuss about the CFD, Computational Fluid Dynamics. And Computational Fluid Dynamics is a science that, with the help of digital computer, produces the quantitative predictions of fluid flow phenomena based on the conservation law like conservation of mass, conservation of energy, conservation of momentum, which governing the fluid motions. The conservation of mass law states that mass entering in the pipe or in control volume should be same or equal to the mass leaving the pipe, and the conservation of momentum, or in other words Newton's second law of motions, F is equal to ma. This prediction normally occurs under those conditions defined in terms of the flow geometry, the physical property of fluid, and the initial and boundary conditions of the fluid. The question arises here why we should study the CFD. Or imagine a case you have to gather the data of rocket exhaust in the freezing winter, or you have to design winning Formula 1 car where aerodynamics play an important role. Fluid is generally literally everywhere, from our to morning toothpaste to in raindrop, driving boat, or in bullet train, literally everywhere. That's why the scientists and engineers exploring more and more this field. The CFD include steps like modeling, discretizing, solving, and post-processing. But these are the basic steps: modeling, discretizing, solving, and post-processing. First, you discretize your model into different parts. Here we divide our model into smaller number of parts, and each part is behave like its own. And finally, you're matching better your result. Both conservation of mass and conservation of momentum equations together called Navier-Stokes equations, and these are in partial differential equations, and both equations are highly coupled. That means you cannot solve one without other. And also these are non-linear equations, which makes them near impossible to solve. To convert these non-linear equations into linear algebraic equations which are easy to solve, different method or approach are used into solver. Before we jump into the different methods or approach, let us take a look back to the 18th century. Even before the Navier-Stokes equations were properly derived, people discussed the physical problem like fluid flow in a mathematical manner. Two men in particularly, the Leonard Euler and Lagrange, has quite different view when it comes to observing the fluid flow. This is important even today, as CFD models are either classified as the Eulerian or Lagrangian method. Using the example of flowing rivers, Euler wanted to observe the river while standing still, and Lagrange on the other hand preferred to dive into the river and then look around himself while drifting with the current. Most Eulerian methods utilize mass to describe the fluid domain. If the mass is not changed, these cells and their neighbors stay the same throughout the simulation. Most Lagrangian methods, on other hand, do not use the mass but rather point which that can move around freely in space, and as these points often carry mass and volume, they are called particles. Imagine each molecules of water in the river as a particle, and these particles can then move with the flow, and these neighboring particles are changing constantly. Now let's discuss the different approach we use in solving. First is a finite volume method. Finite volume method is probably the most prominent method in CFD, and it can be used for the various applications ranging from simulating fluid flow around airfoil to the thermal simulation of conjugate heat transfer to estimate heat flux. The basic idea of the FEM is to subdivide the whole domain into small control volumes, and these volumes exchange flux with their neighbors who are the respective connecting phase. Since the fluxes that enter a cell are leaving another cell, this approach is strictly conserved with the make it very attractive for fluid flow problem. Unfortunately, it is very difficult to increase the order of accuracy of FEM. Second is the finite element method. Many associate the terms finite element method with the solving structural mechanics problem. On contrary to these common misconceptions, the FEM can be used to discretize any partial differential equations, including the Navier-Stokes equations. FEM is actively used to solve fluid flow problem, for example in the field of the external aerodynamics. For the FEM, the space is subdivided into the connected elements. In each of these elements, the solution is approximated by piecewise polynomial functions, and these are defined by the set of basis functions for every nodal point, and this can be utilized for the estimated derivation. Next is the finite difference method. The finite difference method discretizes the Navier-Stokes equations on the set of points that hold the physical variable of the fluid, for example pressure and velocity. These points are usually distributed regularly, as this makes things much easier for the implementation. To compute the derivative at node, and Taylor expansion is utilized. Next is the smooth particle hydrodynamics. Like the other methods mentioned, the SPH discretizes the Navier-Stokes equation to the simulate fluid flow, and the SPH is the Lagrangian particle based discretization scheme. Instead of using the mass, particles are moving around based on the velocity velocity, and the derivatives of the physical quantities are approximate by weighting the quantities of available neighboring particles. As the particle-based method, SPH is especially very suited to deal with the flow that are influenced by heavy deformations like breaking a wave at the beach. Multi-phase flow can also be treated easily as the moving interface between different phases is tracked inherently. Even moving boundaries and the free surface flow are treated efficiently. Hence, the SPH methods enable the flow simulations of use cases which are impossible to simulate before. There are different CFD simulation software available in the market like ANSYS, OpenFOAM, SimScale, SolidWorks, etc. CFD analysis software allow you to visualize and analyze problem concerning fluid flow, heat transfer, etc. in your product design. You can solve these issues quickly and accurately to enable safer and quality product designs and development. I hope that this video helped to gain the fundamental of CFD and approaches used in the predictions of fluid flow. If you found video informative, please show your love with likes and subscribing this channel. See you in next video. Till keep learning and keep exploring.